So new section, the elements of Galois theory. So let's see what we are going to have in this section. Here we are going to consider some polynomial px, any polynomial over our base field f, and we are going to associate with any such polynomial a group called its Galois group. The Galois group of Px. In spite of having this spelling, it's the name of a mathematician. The pronunciation is this. Okay. Now, there is a close relationship between the roots of Px, that is those field elements which if you put here, you are going to get 0. We already know what roots of a polynomial are, and those roots may not all lie in f itself. So, between those roots and the group G, there is a close relation. And in fact, the group G will turn out to be a certain permutation group of these roots. And more precisely, we are going to do this. We will consider the splitting field of Px. Say E is the splitting field of Px, which by now we know that it exists for any Px, and it is essentially unique. We already have seen these things in the previous sections. And now the Galois group of Px will in fact be a certain group of automorphisms of this field E. G will turn out to be a group of automorphisms of E. We have already seen automorphisms of groups. We have seen it in group theory. But we are yet to see automorphisms of fields formally. We will see that. Okay. Now, the fact is that there is a fundamental duality between the subgroups of G on one hand and the subfields of this splitting field E on the other, and there is a relationship between these two kinds of things. We will see this and we will prove the claims in this statement in the fundamental theorem of Galois theory. That's what our main aim will be. And once we do that, using that connection, using that relation, we will derive a condition for the solvability of this polynomial equation by radicals in terms of the algebraic structure of this group, the Galois group of Px. This group will tell us whether such an equation is or is not solvable by radicals. And here I must say some things about solvability, at least some things roughly. You see, this is one thing that we have come across, and in fact we were introduced to solutions of polynomial equations right when we were introduced to algebra. Okay, right from that time we know this thing. In school, in fact, when we learned about algebraic expressions like this, then the equations soon follow. So the linear equations look like this, and for the sake of simplicity, let us consider a and b to be just real numbers, where for this equation to be linear, we need a to be non-zero. Now we know very well how to solve this equation. This equation has the only solution minus b over a. Now if you want, you can treat this itself as a formula for the only root of this equation. If one goes one step ahead, one has to consider quadratic equations, where again for this equation to be quadratic, a is non-zero. Here also say a, b and c are real numbers. Now we are taught in school the various methods of solving such equations, and among those methods the fastest one is the one which gives us the direct formula. And we have used this formula so many times that we know it by heart. Here the two roots are given by this expression. I mean, within this expression itself there are two expressions depending on this sign. Now if one continues this, then there exist such formulas for cubic polynomial equations and also for polynomial equations of degree 4 biquadratic equations, but they are complicated, okay, and they are usually not used that much. However, the fact is that they exist, but starting from the 5th degree and going to higher degrees, for a long time mathematicians were unable to find any such formula. So they thought that maybe those formulas are so complicated that they haven't found it yet, but later it was found that such formulas cannot exist, and that's what we will show here. And as a result, one will get the impossibility of solving a 5-degree polynomial equation, that is the classical Abel-Raffini theorem. And as a side result of these investigations, we will also derive the fundamental theorem of symmetric functions. We will see what these things are, okay. Now the thing is that a linear equation, a quadratic equation, a cubic equation and a 4-degree equation, polynomial equations, these are solvable by radical, which means existence of such formulas. What do those formulas involve? They have the coefficients that are there in those polynomials. Besides that, there are the 4 operations of addition, multiplication, subtraction and division that are available in the system of real numbers. And besides that, we take square roots. Okay, so that's why solvability by radicals. Okay, so this is what solvability means. So we are going to do all these things. Now let me also draw your attention to something else before we start the things properly. We said that the fundamental theorem of Galois theory establishes a relationship between the subgroups of the Galois group and the subfields of the splitting field. Now this is the kind of relation which is somewhat different from the things that we have seen so far in algebra. So far what we have seen, relationships between two structures of the same type, say a homomorphism between two groups or an isomorphism between two rings, group on this side, group on that side, or rings on both sides, or vector spaces, algebras over fields, okay, or fields. This type of relation is, however, between two different kinds of structures. And such relations are found elsewhere in mathematics as well. For example, if one goes to algebraic geometry, or say one goes to algebraic topology, then one associates with topological spaces groups, fundamental groups or homotopy groups. So such relations are there, and there is an area of mathematics in which such relations between different kinds of structures are studied, and that is category theory. Okay. If it is possible, we will study it sometime in future. But let us now start our main thing. So the first thing we are going to recall is that all our fields are going to be of characteristic 0, so that we can freely use those two results from the previous section on simple extensions. Let us recall those two results, because sooner or later we will have to use them. Two results means one of them is the main result and the other one is the corollary. The result says, I think it's theorem 1, theorem 551. So it says that if f is a field of characteristic 0, you can go back to the previous section and see if f is a field of characteristic 0 and a and b are two elements in some extension of f which are algebraic over f, then the extension of f by adjoining a and b is actually a simple extension, because it is also equal to the extension f of c for some c belonging to this extension. And the corollary to this result says that any finite extension of a field of characteristic 0 is a simple extension. So these results are available to us for use. Anytime we need them, we are going to use them. So that is our convention, that all the fields we are going to consider will be of characteristic 0. Okay, so we said that the Galois group of a polynomial is going to be some group of automorphisms of its splitting field. So that means automorphisms of field have to be studied. So let us define automorphisms of fields. Suppose you have a field K and you know that it is of characteristic 0. That is there in the background. Okay, we are not going to mention this anymore. So there is a field K and automorphism of K is a function, say sigma from K into K, such that number 1, sigma is a ring homomorphism. That is one thing. That is, sigma preserves addition then sigma preserves multiplication. And the third condition is that sigma is onto. This is how it's given in the text, and it may be a little surprising. Surprising because Where is one-to-oneness? We are saying an automorphism. From our experience with automorphisms of groups, we know that automorphisms not only should be structure preserving, but they should be bijections, okay, one-to-one as well as onto. However, here we only see onto-ness. So does it automatically mean that it will be one-to-one? In this case, it will be. Let's see how. Suppose you have such an automorphism, and by definition it is onto. We want to show that then it has to be one-to-one. What you do, you consider the kernel of sigma. You know that there is a kernel means kernel of what? I mean, in what sense? It is after all a ring homomorphism, right? So it's a kernel. And we know from that fact and the theory of ring homomorphisms that this is an ideal of the domain ring. In this case, the domain and codomain rings are the same, and it's a field. And we know that a field has precisely two ideals. One of them is the zero ideal and the other one is the field itself. So now the kernel is either the zero ideal or the kernel is K. Now, can the kernel be K? What does it mean for the kernel to be K? The kernel consists of those elements in K that are mapped by sigma onto the zero element of K. Or in other words, the kernel is the inverse image of 0 under sigma, sigma inverse 0. Now, if this is equal to K, then it means that sigma maps every element of K onto 0. However, there is one element, at least one element in K, no matter what K is, there is at least one element in K which is not 0, and that is the unit element. So if this is the case, then the unit element is not there, okay. The unit element is not there where? It is not there in the image of sigma. That is, 1 is not going to be the output for any input under sigma. But then sigma fails to, so that is 1 does not belong to K sigma, the image of K under sigma. So that implies sigma is not onto, which contradicts this. So that is why this case does not arise, and that's why we must have kernel of sigma equal to 0. But when that happens, you already know that sigma has to be 1 to 1. When the kernel is 0, then it has to be injective 1 to 1. So that's why, as a consequence, sigma is also 1 to 1. It's a consequence of all these things and the fact that our ring is a field. And this also tells us that in order to prove that such a function is an automorphism, it's enough to prove only these three things. One-to-oneness is a necessary condition. It's a necessary consequence. All right. So now we are going to next see the first result, in fact, which tells us what happens when we have some distinct automorphisms of a field. So this is a theorem itself, it's not a lemma. Let K be a field and these are be distinct automorphisms of K. Okay, any number of automorphisms, but they are distinct. No two of them are the same. Then it is impossible to find elements A1, A2, that same number of elements in K, not all 0, such that A1 u sigma 1 plus A2 u sigma 2 and so on plus An u sigma n is equal to 0 for all u in K. The statement has to be first understood properly. The way it has been given here may be a little confusing, but keep in mind that this somehow looks like linear independence of vectors from vector space theory. For all u in K. So what the statement says is that if these are distinct automorphisms of K, then we cannot find exactly that many elements in K, not all of which are 0, for which this condition is true. In other words, if such a relation is to give us 0 every time for all u, then all the ai's should be equal to 0. We cannot find a set of ai's in which some are non-zero and still this is true for every u in K. That is not possible. So let us now see the proof. So the proof is by contradiction. We will claim that no, this is false, that it is possible. Suppose there exists this in K, not all 0, such that such a relation is possible for all u. You may be a little confused with this notation. I mean, you already, of course, having come to this stage in Herstein, you know what this means. It is the image of the element u under the automorphism sigma 1. However, in the text you will see that the author has written it like this. In fact, Herstein himself mentions in the section on functions that he is sometimes going to use this notation and sometimes this notation. I really don't like this non-uniformity. I have decided to use in this book consistently this notation only. Okay, so that way it differs from the text. Nothing changes essentially, but I just thought of mentioning it to you. Alright, so we are supposing, contrary to what is being claimed, that such is possible. Then such a relation like this exists with as few non-zero elements, these elements, as possible. So the thing here is that we are saying that it's possible to find a list like this of field elements for which these things will be true. Then maybe there are many such lists. Now among those lists, you see, we are not saying that all the AIs are non-zero, but all the AIs are not simultaneously zero, which means that there is at least one non-zero AI, but maybe there are zero AIs in a list. So among all such possible lists of these elements for which such relations are true, you can find a list which has as few non-zero elements as possible. There is at least one non-zero element in every such list, but with the fewest number of non-zero AIs. That also we will also come across one such list, and this fact comes from the well-ordering principle, which says that every non-empty subset of the set of natural numbers has a least element. It comes from that. So let us now consider one such relation in which the number of non-zero AIs is the minimum. Suppose is such a list or collection, anything you can write, a list of such elements in which there is the minimal number of non-zero elements. Hence, A1 U sigma 1, because it may not actually be this n, so we changed it m. We know that m is less than or equal to n in any case. AM U sigma m is equal to 0 for all u in K. And note that because we are considering this to be the minimal such list, so all the AIs are non-zero. Why? In this minimal list, all the AIs that we see here are non-zero. Why? That's because if there is any zero in any such list, then we can discard the zero, or if there are multiple such zeros in such a list, then we can discard those zeros and keep only the non-zero element. Remember, any such list has at least one non-zero element, because not all of them are 0. So that will reduce the list, reduce the number of non-zero elements in the list. What I'm saying is that it will reduce the length of the list. So the minimality will be violated. So that is why all these AIs now are non-zero. Perhaps I should have written it here. Okay, let me write here itself. And each AI is non-zero. Okay, we are now somehow going to use this minimality, but before that, let us see what happens if m is equal to 1. Who knows, m may be 1, but something will go wrong in that case. If m is equal to 1, there is one more simple thing that I forgot to mention, that you may have to renumber these things. Okay, these numbers or the parameter, you understand, they may not appear in the order or in the way we have numbered them originally. See, what will you do if you are really trying to find such a minimal list from a list that already exists? What will it be? Say some of the elements here are 0, you will then remove them. So say A2 is 0, then the next A3 is non-zero. So A2 will be removed from the middle, and after A1 you are going to write A3. But that's not how this list is appearing. Here we are continuing to write A1, A2. So that is you have to renumber them. You have to call them by some other names, say B1, B2, like that. So there may be a renumbering involved in this process of finding the minimal list. Okay, so that is there. I'm not writing that again. So instead, let us now see what happens if m is equal to 1. If m is 1, then the relation continues to be true. Then, however, it now reduces to this. A1 u sigma 1 is equal to 0 for all u belonging to K. Now we know that sigma 1 is onto, in fact that is there in the definition of sigma 1 itself. It is 1 to 1 also, but we are now going to use the ontoness of sigma 1. Since sigma 1 is onto, so 1 which we know exists in K is going to be the sigma 1 image of something, some u. One is equal to u sigma 1 for some u in K. Then what do we get from this? Writing it slightly differently, we start with 0. 0 is equal to A1 u sigma 1 for that particular u. For every u it is true, so for that u also this has to be true. However, this is A1 times 1, so that is equal to A1. But is it possible? In this relation, there must be at least one non-zero AI. Well, in fact, in this case, the only AI is A1. And because all of them are non-zero, in this case, due to minimality, A1 is non-zero. Here, however, we are getting A1 to be 0. A1 has to be 0. but that is a contradiction. Hence, we cannot have m equal to 1. That is, we must have m greater than 1 because m is a positive integer. Now, because m is greater than 1, and originally we considered the hypothesis that the sigmas are all distinct. So, sigma 1 is different from sigma m. So, these two automorphisms differ at some point, some field element. So, C sigma 1 is not equal to C sigma m for some C in K. Okay. And now we are going to use this element C in this relation itself, in this general relation. Note that now the relation says that I can use any field element u here. Now in place of u, I can also put cu, because that is after all also a field element. For any u in K, cu is also in K. So note that A1 cu sigma 1. Here the parentheses are used to indicate the fact that we are applying sigma 1 on cu only, and A1 lies outside. This is understood, okay? Plus A2 cu sigma 2, and like that, plus Am cu sigma m is equal to 0 for all u in K. And this implies because the sigmas are automorphisms, and so each one of them preserves multiplication. So this implies A1 times C sigma 1 times u sigma 1 plus A2 times C sigma 2 times, why do I keep writing C, u sigma 2 plus Am C sigma m times u sigma m is equal to 0 for all u in K. Let us give these two relations some numbers so that we can now say clearly what we are going to do next. Say we call this one 1 and this one 2. So now what we can do, we can keep in mind that these are not two equations, but actually these are many equations because we can change u. However, we have these things. So now what we can do, we can multiply the first equation by C sigma 1 and subtract from the second equation. So we are going to do this, writing somewhat casually like how we normally write in, or we used to write in school. C sigma 1 times 1. So what will this operation give us? It will give us a new set of equations. So let us first write all the things down and then see what are the things that get cancelled. So first we have this entire thing. A1 C sigma 1 U sigma 1. It does not hurt to write these things. It takes some time, but at least we won't make mistakes. Okay, we can write it like this. Plus A2 C sigma 2 U sigma 2 plus AM C sigma M U sigma M minus. Minus C sigma 1 times this, right? So A1 C sigma 1 times U sigma 1 plus A2 times C sigma 1, do not write sigma 2, okay, that will be a mistake, times U sigma 2, and like that it goes AM times C sigma 1 times U sigma M. It's very easy to make some mistake here. I hope I haven't done anything like that. And this is equal to 0 because we have 0 on both sides. In both the equations. Alright. So now the first two terms get cancelled because they are the same. However, what about the other terms? Taking common elements outside using distributive laws, we get A2 times C sigma 1 minus C sigma 2 times, here also you have U sigma 2, here also you have U sigma 2. And there will be other terms also, and the last one will look like this, minus C sigma M. U sigma 2 is equal to 0. And in order to understand that we are really doing it for all U in K, we keep on writing this part alongside these equations. And now let us look at this final equation. This is again, if you look carefully, this is again a relation like the original one. What was the original relation? It was this, right? A1 U sigma 1 plus A2 U sigma 2 plus AM U sigma M equal to 0 for all U in K. This was our original relation, and we claimed that it was the smallest, having as few non-zero coefficients as possible. However, what about this one? Now, it does not immediately look like this one, but you can make it look like this one by giving names to these coefficients. Say you call this coefficient B2. In order to avoid unnecessary confusion, let us call this B2 and not B1. Sigma 2 plus there are the others also that follow, B3, B4 and so on, and finally we get Bn U sigma M is equal to 0. for all u in K. Now, can we say something about these Bi's? Most of them we don't really know whether whether they are 0 or non-zero, but let us look at Bm. What is Bm? Bm is Am times this. Am is non-zero. In fact, all the Ai's are non-zero here, that we already concluded from the minimality of the length of this equation. C sigma 1 and C sigma m also are different. You remember, that's how we chose the element C, and that's why their difference is non-zero. Now Am is a non-zero element in the field K. This is non-zero, so their product Bm is also non-zero. And that's how we have found, and this is also true for all u in K, we have found another relation which has shorter length than this one, and where also not all the coefficients are 0. But this directly contradicts the minimality of this relation. And that contradiction proves that our original supposition is wrong. Namely, we cannot have such AIs in the first place. And that completes the proof of this theorem. We will see how this theorem can be used later on. But right now, let us define something. At this very moment, it's quite difficult to understand how this theorem can possibly be used, but it's a very important thing. And in fact, it is important, that's why it's a theorem and not simply a lemma, because the result itself is not very difficult in terms of statement or proof. Proof is also pretty straightforward, but it is important. Now the next thing is this: definition. These are things that we will need. So the next definition is the definition of a fixed field. So let K be our field which has characteristic 0, that thing is there. Let G be a group of automorphisms of K. So K is there, K has all the automorphisms that it has. From among them, we have collected some automorphisms so that they form a group. Let G be such a group of automorphisms of K. The fixed field of G is defined to be the set of all those elements A in K that are fixed by every element of G. Remember, the elements in G are automorphisms of K. So each one of them can be applied to this A. Now if each one of them keeps A fixed, that is, does not change A, then A belongs to the fixed field of G. A sigma is equal to A for all sigma in G. It's a pretty straightforward idea. No matter how many elements G has, you collect those elements from K which are unchanged by all the elements of G. Then the collection is called the fixed field of G. By definition, that collection or the fixed field is going to be a subset of K. Now here there are two questions that are arising. The first is, we are calling it the fixed field of G. Is it really a field? Yes, we can prove that it's a field. It's pretty straightforward. The other question is, we do not see the fact that G is a group playing any role here, and in fact that is true. There is no need to consider G to be a group. Here in place of G, you can just consider a set of automorphisms of K. Then also this definition makes sense. That is true. However, there is a fact for which we have considered groups here. It's because if you consider a set of automorphisms of K instead of a group, I mean this S is not necessarily a group but merely a set of automorphisms, then it turns out, well, the author has not given any notation to this fixed field, but just for the sake of saying what I am now going to say, let me just call the fixed field of G, say, let me denote it by this notation, F suffix G. It denotes the fixed field of G. Then for a set of automorphisms of K, S, it turns out that the fixed field of S, if you would have defined it for a set of automorphisms instead of a group, correspondingly you will have Fs. It will consist of those elements in K which are fixed by every automorphism in S. It turns out that this is the same as the fixed field of the group generated by S. You know that K has automorphisms, and the collection of all of them, it turns out, forms a group. And in that group, this S is a subset. So, as a subset, S will generate a subgroup. It is the smallest subgroup of the group of all automorphisms of K that contains S as a subset. Because of this, we decide to not define Fs for an arbitrary subset S but only for groups. And besides that, we also have the fact that we will have occasion to consider only fixed fields of groups of automorphisms, not merely sets of automorphisms. And this fact we will prove in exercise 1. So let us now quickly see this, the justification of calling it a field in this next lemma. Next lemma means it is the first lemma of this section. The fixed field of G. In the context of this discussion, we are writing the statement like this. Just by itself, this will be meaningless. Okay, what is G? The fixed field of G is a subfield of K. So this is the problem when we do not put notations to these things. You have to keep on writing words I really dislike that. Instead, let me use this itself. So we need to prove that Fg is a subfield of K. Now before we do anything with Fg, we need to first make sure that Fg is a non-empty subset of K. By definition, it's a subset of K. However, is it non-empty? Yes, it is non-empty. Why? Because it contains 0. Why though? How exactly is 0 an element of Fg? Is 0 fixed by all automorphisms? Yes, because an automorphism is after all a ring homomorphism, and any such function maps 0 to 0 itself, and that's why 0 belongs to Fg. Now next, say you take the rest is usual, A and B in Fg, then A sigma is A and B sigma is also B for all sigma in G. So this in a pretty straightforward manner, this is going to imply that such is also the case with any such combinations. A plus or minus B stays like that. AB also stays like that, it stays AB, and B inverse sigma, which by properties of automorphism is the inverse of B sigma, but B sigma is B, this is B for B not equal to 0. Hence, the sum and difference and product belong to Fg, and the multiplicative inverse also belongs to Fg if B is non-zero, that is. And that's why Fg is a subfield of K. So it makes sense to call it a field. Now there is a kind of an, should I say, an opposite definition. You see, in this definition we started with a group of automorphisms and we defined a subfield of K. But what if we start with a field and then define a group? So the next definition is that. Do you see that in these definitions already we are associating groups with fields, fields with groups? So this will set up that association we were talking about in the fundamental theorem of Galois theory. Let K be an extension of F. So now we do not start with a group, but we start with a field and an extension K of F. The group of automorphisms of K relative to F is defined to be the set of those automorphisms sigma of K for which alpha sigma is equal to alpha for all alpha in F. That is, now it is as if we want F to be the fixed field, and we are, instead of collecting field elements for a given group of automorphisms, now field is given, and we want to choose those automorphisms from the collection of all automorphisms of K that will fix all these field elements. I mean, not all the elements of K, but all the elements of F of the base field. Then that group is called the group of automorphisms of K relative to F, which keeps F fixed, or rather its elements keep F fixed, and we denote it by this group of automorphisms of K relative to F. Now, just like the fixed field had to be proven a subfield of K, here also note that we have defined it as a set of automorphisms, but here also it will turn out to be a group. In fact, it is a subgroup of the group of all automorphisms of K. This fact is only stated and not proved by the author. I am also not going to prove it, I leave it to you. Instead, let me just write the formal statement. It is extremely easy. Oh, by the way, when we say group of automorphisms, do you realize what the binary operation of that group is? It is simple function composition, just like you have in the group of automorphisms of a group. Okay, just like that, here also the binary operation is composition, because that is the only sensible one in this situation. So this is the second lemma. GKF is a subgroup of the group of all automorphisms of K. Okay, the proof of this lemma is your homework. And that's just it for tonight in this video. In the next field theory video, we will see properties of this group, and we will somehow, you may guess, we are somehow going to link this with the fixed field of something. And one of those properties, let me just mention one that we are going to see, which is going to be very important, is this. If K is a you see, in this definition, K is simply an extension of F, not necessarily a finite extension. As a vector space over F, K may not be finite dimensional in this definition, but if it is, if the degree of K over F is finite, then it turns out that this group is also finite, and its order is less than or equal to this degree. We will see this in the next field theory video. And our next upload is this, when do we have? Tuesday, no? Tuesday, Thursday, Saturday and Sunday. So on Tuesdays we have our usual group theory from Herstein. Now because we have already completed the theory part from the section on Silas theorem, so on Tuesday actually we do not have a video, but instead we will start solving exercise problems in the community section. So see you on Tuesday with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.